Hello guys, in this part we will try to explain how we could calculate or determine or estimate the power which are carried by an electromagnetic wave which are already in a propagation situation or in a propagation status. That's mean, for example, we need to calculate or estimate how much power or how much the energy of the electromagnetic wave which are propagated from a certain satellite, okay, or from the sun or from a galaxy, okay. So now we are talking about electromagnetic wave propagate in a certain media, and this media is unbounded. So from this electromagnetic wave, it's too hard to calculate the total power because we know in unbounded the power is propagated or is traveled in all direction, okay. So it's too hard to determine or to calculate the power directly, okay. So for such case we will calculate what is called power density. Power density, okay, give us an information about the power or the propagated power but per unit area and at a certain direction. So if the source of the electromagnetic, okay, propagate electromagnetic wave equally in all direction, so maybe we could use the power density, okay, to calculate or to demonstrate the power, okay, and we will see that in next example maybe. But in case of the propagation in unbounded media and the propagation from the source or from the unknown source is non-equally in all direction, so in such case it's very hard to calculate the radiated power and we need to calculate the power density. Power density, that's mean power per unit area, that's mean power incident on a certain area in space and in a certain direction. So this parameter is calculated by the cross product between the electric field and the magnetic field. As we are talking about cross product, so the product of this cross product will be vector also. So according to that we say the power density refers to the power per unit area and at a certain direction. So we call this by pointing vector and refer to it by S, capital S letter. So this is vector represent the power density, and we could calculate it by cross product between the electric field and the magnetic field. So its unit, it's equal watt per meter square because it's volt per meter, cross product ampere per meter, meter per meter, meter square, volt per ampere times ampere, watt, and its direction normal on the electric oscillation direction and the magnetic oscillation direction. So as we said, if we need now to calculate the power from the power density, okay, so for example we need to calculate the power which are delivered by an antenna or by any receptor or any receiver. We need to integrate this power density for the area or the aperture area of this antenna or of this receiver or an receptor. Okay, and if we need to calculate the power which is radiated from a source, okay, the total power which is radiated from a source, if we need to calculate this power, for example, if we say this power is represent the radiated power from a source and we need to calculate it by using the power density, so according to that, this radiation, it should be isotropic. Okay, this radiation, for example here, it should be isotropic, and then we could calculate this power density to the area of the space or any space surrounded the radiator or surrounded the transmitter, and then calculate how much power radiated from this transmitter, but in condition that, say, the radiation, it should be isotropic. Isotropic means that the propagation is equally in all directions. That means this transmitter radiated electromagnetic wave by equal amount, by equal energy or power in all directions. So we could use the power density integrated by the area of the space which are surrounded this radiated, and then find how much power radiated or the total power which are radiated by the surface itself. So in this equation we could use the recepted power or the transmitted power in case of the isotropic. The recepted, in any case, we could use the power density which is incident on any area or any surface, and by take the integration for this power density and the area of this surface, for example antenna or any receiver, and then we could find how much power received or incident or delivered to this device or to this component or to this surface. So P equal to the integration for the area of the surface, as it's the power density vector, and the surface here, the surface is also vector. Direction of the surface is n, and the direction of the power density is k. For example, here this is the shape, this is the power density, is direction k, incident on a certain surface, its direction n. So n, it could be applied or typically applied with or parallel with k, or maybe there's an angle between them, so it's very important to know this angle, and then we could calculate how much power will be received or incident on this area by take the integration between the area and the power density. So power, it's equal, if we know this area by A, it's equal to the magnitude of the power density multiplied by the cosine theta between n and k, and in case of theta is equal to 0, that means that k and n is parallel, so this cosine will be 1, and go on. Okay, so according to that we will get power. According to this integration, the power which will be resulted, it's typically equal to the power which is calculated in a transmission line, which is equal to the product between voltage to the current, volt with current, because we will integrate the electric field and the magnetic field. Integration of the electric field with the dimension it's equal volt, and integration the magnetic field with the dimension it's equal current. Okay, so the resulted power is typical to its counterpart in the transmission line case, and we will discuss about the transmission and the power which are carried by the transmission maybe in the future in next semester. So according to the variation of the electric field and magnetic field with time, both of them are quantities which are time varying, so the resulting power resulting from this, or even the power density S or P, both of them will be time varying quantity. So according to that, if we need to specify a certain value for the power density or for the power, of course we need to deal with the average, okay, because this quantity is varied with time. So if we need to specify a certain quantity, certain value, sorry, we need to deal with the average. So the average of the power density, it's equal, of course here we are to deal with now, if we need to specify a value for this quantity, for example the power density, or even for power, of course we need to work or to deal with the instantaneous form, okay, that's mean the time domain, in time domain. So the average is equal half 1/2 multiplied by the real part of the production of the cross product between the electric field and the conjunction of the magnetic field, okay, that will give us the average, okay, value of the power density. And in case of the power, for example the power charge carried by transmission line, same, we are talking about the real part of the product of the voltage times the conjunction of the current. And as we said, we will discuss this in the future. So let's now take an example of plane wave propagates, okay, of a plane wave propagates in a lossless medium or free space or vacuum. So to calculate the power density, as we said, we need to know the electric field and the magnetic field and then find the cross product between them. As we said, in a plane wave, the electric field is expected to have two components, X component and Y component, okay? So we have X and Y, both of them shape a plane wave, and this plane wave propagate in Z direction, okay? So this is first. For the magnetic, we know we have same, we have X component, Y component, and both of them propagate in Z. And because magnetic field is equal to the electric field per the intrinsic impedance, so we could convert this equation for this, okay, to make the relation by just electric field or by just magnetic field. So magnetic field is equal to the electric field divided by the intrinsic impedance. According to this, now it's look like we have plane wave, where we have plane wave with electric field component in X and in Y direction, okay, this is both electric field component in positive X and electric field component in positive Y, this is in red. And the magnetic field, after we convert it to the electric field mathematically, so it's equal or it's equivalent to magnetic field positive Y and electric field in positive Y and electric field in negative X, okay. By take the cross product between, we need to take the cross product between the electric field and the magnetic field. So this is the electric field, red, cross product the magnetic field, which now represented by electric field in blue. So what we get, let's see, of course here we are need to take the magnetic field the conjugate, that means this minus of the exponential will be positive, okay. So the production of the cross product between these two quantities or vectors will give us in Z direction a new vector in Z direction 1 over 2, because we are talking about the average, so there is a half. So 1 over 2 intrinsic impedance, this is from the convert the magnetic to the electric. Okay, Ex naught square plus Ey naught square. So that terms, or this summation between x naught square and y naught square, it's equal to, according to this, okay, it's equal to the magnitude of the electric field. Okay, under square root, it's equal to the magnitude of the electric field. Okay, so according to that, this could be written as a magnitude electric field square, because we are talking about the square of the x component plus the square of the y components. Okay, so if we take the square root for this summation, we will get the magnitude of the electric field, and here we have magnitude square. So we could use this equation or this rule or this formula to calculate the power density or the average power density where in lossless medium. Okay, let's explain here an example of the power density in lossless or in vacuum or in free space medium. So here we have, or we will deal with the solar illumination, okay, from the sun. So here let's talk about the electromagnetic radiation from the sun. Okay, if now we know the power density from the sun, it's equal to 1 kilowatt per meter square. This is the power density of the electromagnetic radiation from the sun. Okay, so, and if we assume that this propagation or this radiation or the radiation of the sun are isotropic radiation, so the propagation is equally in all directions. Okay, and of course we know, or we need to know, the radius of the sun is 1.5 times 10 to the power 8 kilometer, and the earth mean radius, or the radius of the earth, is equal to the 6,318 kilometer. So what we need to know, first we need to calculate the total power radiated by the sun. So here we need to calculate the radiated power, or the total power which is radiated, okay, from the sun. Then we need to know the power which received by the earth, or accepted or received by the earth from the sun. And finally we need to calculate the electric field of the power density incident upon earth's surface. Okay, of course here we have very important assumption that all the power or radiated from the sun is at a single frequency. Let's go now. So A, here we will use the power density to calculate the radiated power. Okay, this is just if we have isotropic radiation, because in such case we could use the power density on the area of the space, okay, which is surrounded, any space surrounded the source. We could use these two quantity to calculate the radiated power. So according to that, we use this power density, okay, and the area of the sphere which surrounded the sun, okay, by using the radius or the distance between the sun and the earth. Okay, yeah, sorry, rs here is not radius of the sun, is represent the distance between, or the the radius of the orbits of the earth surrounded the sun, or the distance between the sun and the earth. So by using this distance we could calculate the area or the sphere area which is surrounded the sun, okay, and by use the amount of the power density, which we know 1 kilowatt per meter square, we could calculate how much power radiated by the sun. Okay, because here we have isotropic radiation. That means the power density here and the power density here and the power density here are equally. All the power densities on this surface are equal. So we could use this power density and the surface area, then calculate the power, the total power. So the total power which is radiated from the sun is equal to 2.8 times 10 to the power 26 or 26 watt. Okay. Now if we need to calculate how much power received or incident on the surface of the earth, so according to that, if we assume that the cross section of the surface of the earth, which will be the surface of the aperture, or the surface which will receive or accept the power from the sun. So we could use this area, the aperture area, okay, the area of the cross section of the earth, and the power density from the sun, okay, and calculate how much power will be incident or will be received by the earth. Okay, so say the power incident here on the earth is equal to the power density multiplied by the area. But which area? The area of the cross section of the earth. Okay, the area here, area of the circle, because now we are talking about the surface which will equal to the surface which received the power from the earth. Okay, and this power is equal to 1.28 times 10 to power 17 watts. So also we could calculate from this relations, we could calculate how much the electric field of this power, I mean the power which is radiated by the sun. So the power density, this is equal to 1 kilowatt per meter square. Here we need intrinsic impedance, and we are talking about the medium between earth and sun. Almost of the medium is a vacuum, so we could use intrinsic impedance for vacuum, okay, which is constant, equal to 377, okay, ohm. This is the intrinsic impedance, and according to that we could calculate the electric field by using all this parameter, which is equal to 870 volt per meter. So in case of propagation in a loose media, the power density same as lossless, except that here we have, because here we have loose media, so we will accept the following extra parameter. First, here we will have attenuation function, referred to how much the power will be attenuated. So it's exponential to minus 2 alpha z, and of course the intrinsic impedance will be complex intrinsic impedance, okay, because we have loose media. So the final formula for the power density in loose media will be equal, the direction of this power density, as we said, it's normal on the direction of E and H, so for example it's Z, magnitude of the electric field divided by 2, because we have average, multiplied by magnitude, okay, of, because here we have complex, so magnitude of the complex intrinsic impedance, all multiplied by function of the attenuation. Previously in lossless this is equal 1 because alpha equal to 0 in free space. Here we have lossy, so alpha is significant, so we need to put this function. And the cosine of theta of the intrinsic impedance, that's because we have, as we said, we have complex intrinsic impedance, and the complex intrinsic impedance, because we have lossy media, it has magnitude and phase. So here we are talking about magnitude and its phase because we work with average, so we need to calculate it in instantaneous form or in real form. So from this exponential we just need the cosine, okay, and then we will get the final expression for the power density in case of lossy media. We need to note here, in case of the electric field and magnetic field, the attenuation function is exponential minus alpha z. Here we are talking about power, so it's exponential minus 2 alpha, and we explained that previously, that the power proportional to the field square, E square or H square. So according to that, the attenuation here will be faster, will be stronger, okay. So the exponential here multiplied by 2, and according to that the penetration depth will be shorter, okay. So we expect the penetration depth in case of the power, it's half of the penetration depth of fields or of the fields. So if the fields reach to about 37%, okay, after 1 over alpha, so the power for the same distance will reach to 40% from its initial for the same distance, okay.